Assalamu alaikum everyone. Hope you all are doing good. Do subscribe, follow and like the channel. So let's begin with our today's lecture. So today we are going to discuss the graphs. Let's first see what graph is. So in computer science, a graph is a collection of connecting nodes or vertices with the help of edges or the links. So these blue dots that you're seeing are the nodes, and these green lines that you're seeing are the edges or links. A node is a thing or an entity to which we can assign some value. So a person, a car or a city, they all are an examples of the nodes. An edge, the green lines that you are seeing right here, they are defined as a relation of some sort between different nodes. A perfect layman's example might be the Facebook. The network of you, your friends, and their friends, etc., are collectively referred to as the social graph. Here, people are the nodes connected through the friendship edges. So that means this particular person is a friend of this particular person because they both have an edge linking them together. Similarly, here we can show connected cities using a graph like in the given figure. Cities are represented as node or vertices, and the roads distance is represented on edges. So for example, from Los Angeles to San Diego, the distance is 100. Similarly, from San Diego to Riverside, the distance is 90. Types of graphs. There are two types of graphs. The one is the directed graphs and the second one is undirected graphs. We will look into both of them one by one. So let's see the undirected graph first. So this is an undirected graph. The edges have no direction. They are simple lines connecting two nodes with each other. So this one is connected with the two. So we say this particular graph have vertices and edges, and the vertices we have 1, 2, 3 and 4 in vertices, and then this particular graph has some edges, like there is an edge from 1 to 2 and similarly from 2 to 1 as well. Because it's undirected graph, so we consider the edge is going both ways, and similarly 1 to 3 and 3 to 1 and so on. We have 1 to 4, 4 to 1, 3 to 4, 4 to 3, 2 to 4 and 4 to 2. The directed graph. In directed graph, the edges have a certain direction. So that means we can only go from 1 to 2 and not the other way. We cannot go from 2 to 1 because there is no edge with that direction here. So in this particular directed graph, we have vertices and edges, and we have vertices as 1, 2, 3 and 4, and then we have some directed edges, such as there is an edge from 1 to 2, then there is an edge from 2 to 4, an edge from 1 to 3, an edge from 3 to 1, 1 to 4 and 3 to 4. So this is a directed graph. The major difference between the undirected and directed graph was very simple. In the undirected graph, the edges are directionless, so we consider them both sides. But in directed graph, the edges have certain directions. Adjacent vertices. So in any given graph, two vertices are said to be adjacent to each other if they have a edge connecting them, or if they have an edge directing to each other. So for example, in this undirected graph, there is an edge between 1 and 2, which states that by following this edge from 1 I can reach 2, and similarly I can reach 1 as well from 2 by following the same edge. So that means in this particular graph, 1 and 2 are adjacent vertices, and they both are adjacent to each other because it's an undirected graph and the edges are directionless, so they go both ways. But when we come into the directed graph, we see here we also have vertices such as 1 and 2, but there is only one edge whose direction is from 1 towards 2. So we say in this particular graph, only vertex 2 is adjacent to vertex 1 and not the vice versa, because there is no way, no edge from 2 to towards 1. So the vertex in this case the vertex 2 is adjacent to the vertex 1, and in this case vertex 1 and vertex 2 are both adjacent to each other. Graph representation. We have two main representations to represent a graph. The first one is called adjacency list representation. In this particular representation, we use arrays of vertices lists. So we contain arrays, and each index of the array represents a single node in a graph, and then the list contain all the edges leading to certain other vertices. In adjacency matrix representation, we have a 2D array, or otherwise known as matrix, where each index represents vertex and the value represents the edge. So let's see an example of both. So here, adjacency list representation. So I have a certain graph whose edges are like 1, 2, 3, 4, 5, and then we have certain edges. For example, from 1, we have an edge that is going to 2. Then we have a certain edge which is leading to us to 5, and similarly there is no other edge that is going from 1 to some other vertex, so we put a slash. That means here is the end of the list of this particular list of the edges of the vertex 1. Similarly, we will keep repeating this step for all the other vertices. So for 2, we have an edge leading to 1, 3 and 4, and similarly for 3 we have an edges leading to 2 and 4, and for 4 we have edges leading to 2, 5 and 3, and similarly we have 5 with edges leading to 1 and 4. So this is another example of the directed graph which is shown in the adjacency list matrix. So you can see here in the F1 list I have only added 2 and 4 because these are the only two nodes which have a direction edge from coming from the 1. So similarly for 2 I have only added 5 because that is the only outgoing edge of the 2 vertex, and this one, that the edge that is coming towards 2, it's the incoming, and in adjacency list matrix we only store the outgoings of a particular vertex. So that's why I have only stored the 5. Hope it makes sense. Comment down if you have any queries. So let's go forward to our second representation, which is adjacency matrix representation. So here is adjacency matrix representation. So we have 1, 2, 3 and 4, 5 some vertices, and I have a 5 cross 5 matrix which has 5 rows and 5 columns, right? So each index, like 1 to 1, it's showing 0. That means there is no way 1 to 1. There is no self loop on 1 to 1. There is no self edge on 1 to 1. So on 1, 2, that means there is a pathway between from 1 to 2. So here we have an edge that is leading to 2 from 1, and similarly in 2 to 1 we also have one that states that this edge is directionless and it goes both ways, so it goes from 2 to 1 as well. And similarly you pick any two nodes, for example 4 to 3, so you will see in 4th row and 3rd column you will see a 1. So that's how we develop adjacency matrix representation. We develop how many vertices we have to that cross matrix. For example, we had 5 vertices, so I had a 5 cross 5 matrix. If you had 7 or 10, you will have the respective cross matrix, and then you will put 1, and in each box where there is a path between the path or edge between the two, and then you will put 1 wherever there is an edge between two nodes. There is another example of adjacency matrix, but with the help of the directed graph. So you see we have 1 to 2, there is 1, that means there is an edge that is leading from 1 towards 2. But the 2 to 1 is 0, that means there is no way back to 1 from 2. Let's move next. Which notation is better? Matrix adjacency list, the adjacency list, or adjacency matrix? Which notation is actually better? It depends on the type of the application. However, adjacency list saves the memory, but it is difficult to determine whether there is a path between two nodes or not. This aspect can be easily covered in adjacency metrics, however, but it suffers as far as space is concerned. So it totally comes towards the type of the application that you are going to be implementing. Facebook actually suggests you friends over time. So Facebook have a whole friendship graph generated, and they are continuously analyzing that graph, and on the basis of your mutual friends and the people that have similar interests with you, or the people that are going to the same institute as you, the Facebook suggests them to you as their friends. So shortest path between two vertices. What if you have a cities graph and you want to find the shortest path between two cities? So here is what we are going to do. We are going to learn a simple algorithm that is being used to actually find the shortest path between two vertices of a graph. So for example, in this, if you want to find our shortest path from 1 leading to 4, we will apply an algorithm. That algorithm is called Dijkstra's algorithm. It's a greedy algorithm for computing shortest path between two vertices or the nodes. So Dijkstra states it works on a weighted graph. Weighted graph means each edge will contain some weight. And if we are talking about the cities, each edge will contain the distance between two particular cities. So each edge will have some weight. So that means all edge weights must be non-negative. The basic structure of Dijkstra algorithm is to maintain an estimate of the shortest path from the source vertex to each vertex in the graph, and at the end, Dijkstra will actually find you the shortest path from one source vertex to all the other vertices. So let's see a working example of how Dijkstra actually works. So in this working example, let's see our source vertex is this particular vertex, that is U. So I have my source vertex as U, and I want to find what is the shortest path and how much the shortest path weight is that leads me to V. Of course, there is a direct path which is 7, but I want to find the shortest one, and similarly the shortest to X, the shortest to W and Z. So let's begin. So first, it's clarified that U, the distance of U from itself will be 0. So we have green that particular vertex to show that we have visited this particular vertex, or this particular vertex has been resolved. So the shortest distance of U from U is 0. Now we will see all the vertices that are connected to U via some edge leading from U. So we have two edges, one is 7 and the other one is 2 leading to X. So because it's priority log, so we will get the one which have the shortest distance, because it's greedy algorithm, so it will always incline towards the shortest one. So we have our shortest one which is 2. So that means to reach to the 2 we have to go from 2 this. So we select that particular edge and we get to the X. So that means the shortest path to get to the X from U contains a weight of 2. Now we need to find the others. So we will begin from here and we will see all the outgoing edges, and we have 1, 2 and 3 edges. So one was going to the V with the 3 weight, the other one was going to W with 8, the next one was going to Z with a 5 weight. So we select the minimum one, which is the V1, X to V with the weight of 3. We select this and we put V as our visited node. So now V has been visited and the minimum shortest distance is 5. So that means if we want to go to V from U, we will not opt this straight path that is costing us 7. Instead, we will take this path, we will go to the X, and then from X we will go to the V, and it will cost us less as compared to this straight path. So now moving on, we will have these edges, V to W, which is 1. So of course, because we are working in the shortest and the greedy path, so we will select this W1. So we will select this, and that means W becomes visited with a weight of 6. So that means if you want to go from U to W, you will go to the X, then V, and then you will go to the W. Similarly, we will repeat this step. From W, there is only one outgoing, that is going to Z, that is 5. And all the edges that are coming from behind, we will select the minimum one and the one that came to us first, and that was X to Z with the same weight as 5. Because we encountered this one first, so we will select this one. So we'll go from X to Z, and we will mark Z as visited, and we have a 5 plus 2 as 7. Now, right now, we have all the vertices as visited. That means our Dijkstra has completed its working because it has traversed the whole graph. Now, if you look closely, we have all the shortest path and their weights. So from U to X, the shortest path weight is 2. From U to V, the shortest path weight is 5. From U to W, the shortest path weight is 6. From U to Z, the shortest path is 7, and so on. Dijkstra algorithm. Here is a brief algorithm of the Dijkstra. If anyone is interested, they can look into this. This particular sign is a pi. So hope this lecture has helped you in understanding the graphs and especially the shortest path between different vertices using Dijkstra algorithm. If you have any questions or queries, please comment down below and I will be happy to reply you. Have a good day everyone. Do subscribe, like and follow the channel. Allah Hafiz.